So which means it will be divided by what? Pages and loaded into the memory, or the page frame will be assigned. However, as we have seen before, heap is dynamically allocate the memory. And the step is temporary, which means this area will, so compare it, if you consider the entire structure of the size of the process, not all of the space, data structure are being used, okay? So for example here, if you use the allocate, dynamic allocate, the heap will be used for what? Array. So even though the instantiate, like the array, like the three-dimensional array, 1,000 by 1,000 by 1,000, all of them are not used right now. Okay, it's allocated, then will be used dynamically, and sometimes it will be revoked free. So which means this is called a sparse address, sparse area, because it's not being used from beginning of process, end of process. So which means why don't we free this space if in case it's not used. So that is the idea of using the virtual memory. And if we consider the address of this one is a virtual memory address space. So another benefit is nowadays we use a lot of such as shared information, shared the library and API, such the data. So in case of the shared library or the shared information, we can use the shared page to reduce, like this one, to reduce the usage of the physical memory. And also another benefit is a demanding page. Demanding page means we don't need all the pages at the same time at the beginning. Instead, as needed, we can bring the page needed into the memory. The others will be in the virtual memory. So that is also the demand paging. Okay. So this is called the lazy swapper. Lazy swapper means if some of the page is not being used, then it will not be swapped in, page in forever. So that is called the page the lazy swapper. Okay. So sometimes we call the page. This is the swap in and out entire. But if we consider the page by page, this is called the page out and the page in to the physical memory. So this is a virtual memory. This is the physical memory. So at that time, do you remember one of the critical the problem of managing the memory is what? Protect. So the reason is that if you know the address of the memory, you are able to access the data, because the memory itself is nothing but just the sequence of addressing. So to protect such information, to protect the process, we consider base and limit is a boundary. However, that makes sense to only the chunk, contiguous allocation, or a segment. The segment is a big chunk of the process, so it makes sense. What about the page? So page, we don't have the starting and the end. Okay, it's not like the boundary. Instead, it's a page by page. So to protect that one, we used what? The valid, invalid bit. So we can use the valid, invalid bit in the virtual memory. Problem is, what if this page virtually is in the memory, but physically some of the pages are not in page frame. So CPU cannot read the data. We need to bring into the demand paging or whatever. We need to bring in that page to the physical memory. So how do we decide? We need to check each and everything. At that time, we can use a valid, invalid bit. So if invalid, which means operating system regard invalid bit, that page is in the swap space. So we can bring that to the memory. So we can implement to such a virtual memory using the valid, invalid bit in the memory management unit, MMU. So this is the little bit the details of the page table from the schematic diagram of the pages. So you can see that this is a program, your program. This is a physical memory. This is a virtual memory space. And this is a page table between the logical memory, your program, and the physical memory, but it has more. It's a valid, invalid bit. So for example, right now we are using 0 and 2 and 5. 0, 2, and 5 on demand paging, which means loaded into the physical memory, ACF 469. So we have the 0, 2, 5, 4, 6, 9. So it's a paging table. So whenever you need to read the instruction from this one, it will be okay. However, what if the A? A is okay, but the B. So CPU would like to read the data from the B, but it's a page number 1. 1 is invalid. Invalid means it's in the virtual memory. So we need to bring in one of this free space. Okay, so page in and page out, and using the valid, invalid. So in case you cannot find the pages, or if that is invalid, that is the interim. Specifically, it's a try, like the exception. So in the programming, so try and catch. Okay, if something happens, the try and catch is called error handling, but it's not always the really problem or mistake. So whenever you catch the event, okay, realize the event, then do something. It's kind of event, condition, and action, the process, ECA process, same thing. So in case we found such the invalid, then we raise the trap, then do something. Do something means run the page replacement algorithm in the operating system. That is called page fault. So page fault means if you cannot find, in other words, if your page is set as the invalid bit, that means it's a page fault trap, page fault interim. So in case of page fault, we need to do what? By the way, where is this one? In your operating system, especially the number of interrupt. So it will be defined. And each the interrupt has the action program, small program that will be invoked, that will be run. So that is the page fault. That program we will discuss in the page replacement algorithm. Okay, so let's see this diagram to understand. For example, we'd like to read the data M. But M, we need to first check the page table. Page table, M is the set as invalid. Invalid means it's not in the physical memory. It's in the virtual memory. So you need to raise the program that is the replacement. So that replacement read the data from the swap space, virtual memory space, is M is here, and bring into the physical memory. However, in case there is no free space here, there is another thing you need to do. That is a replacement. But we don't discuss yet. So if you have the free page frame, okay, then load it into the here. Then you need to update page table. Okay, then this one will be set as a valid and the mapping between logical memory and the physical memory. Then finally, continue the instruction. This is how it works in the in case the page fault. So this is called the page fault, and using this one, we can this is based on the demand paging. Demand paging is instead of load all the page into the physical memory, so we can load only needed. So that is the demand paging. Okay. So this one shows all the state, the step of the demand paging. That's what we have discussed before, but it's described as a step by step. You can read, then can understand. Then we can calculate the performance of such a demand paging. So that is evaluated by the effective access time. So how many of them are from the memory access? And the 1 minus p means what? There is a percentile, okay? The ratio of accessing the page from the memory, 1 minus p is the page fault. Okay, so in case the p is equal to 0, no page fault. All of them are in the physical memory. Otherwise, we need to calculate what? The overhead of the page in and out. So page fault overhead is some little bit latency to raise the trap, page fault trap, then call the program, and the more important thing is the page in and out, the overhead. Ideal case is, in case we do not have the page fault, that will be the ideal case. All the pages are in the memory. It's ideal, but not always. It's we need to have such a page fault overhead. So I'm going to skip the example of such a demand paging, the effective access time, but you can easily calculate how much different depending on the percentage. Which means the P is the very important to in terms of the administrative job. So the administrator check the P, how many page fault in your system, and the minimum such a number of pages. Then let's check my virtual machine. So there are several commands that you can check how many page in and out or page fault. One of them, most popular one, is a VM state command. VM state is called the virtual memory statistics. Virtual memory is this one. Then if you give the number, like the 2, is every 2 seconds is updated. So you can see. So this is not only for the virtual memory. Actually, give the overall the performance statistics. Is one of the very good. I use a lot of this. So for example, the left-hand side is the processes. How many running process? How many of them are the blocked process? So you can see because there's nothing. No process are currently running, so it's a 0. Then this is for the memory. This is a swap. Swap means what? Page in and out of the virtual memory. So do not ignore the swap when you see, especially the Linux-based system. Unix-based systems still use, most of them use the swap instead of the pages. Then this is a physical I/O. It's an I/O device. Okay. Then this is the CPU. CPU means, do you remember? There are US. US is a user. System either way. What does that mean? User and system. It's a dual mode. Kernel mode and user mode. So this user is a user program. How much CPUs are being used for user mode. And this is the kernel mode. Idle is idle. Then the wait time will be here. So this is, in this case, the virtual machine not doing any job. Because of that, most of them are idle. But you can see that sometimes the user program, because it's a user program, and some of the system library kernel mode will be used. So when you monitor the system, the operating system, this user and the sys mode is balanced. Okay. If one of them has a huge number percentile, that's the problem. Always you should have something balanced. It's mostly 1 to 2 or 1 to 3, the ratio. That is what are the weight? It's I/O weight. So some of the process are waiting for I/O, so it's the I/O weight here. Then finally the memory part. It's free means physical free space, and buffer and cache. And how many of them are cached and the buffer? So you can see this part, how the free space. Okay. Then Swapped means how many of them are in the virtual memory. So it's very less. So this time we don't use a lot of the swap. Then if you have something running job, you will see the SISO. SI is a swap in, it's a page in and page out. So which one is better? Swap in is high and the swap out is low. Or vice versa. Swap out is high, swap in is low. Which one is better? So both of them are problem. Okay? You do better, keep the less number of swap in and out. Whenever you have the number of swap in, page in and out, which means it require physical eye. Okay? So that is the kind of the criteria to judge whether your system is good performance or bad performance. So from this swap page in and out statistics. Similar thing you can find. So this is one of my favorite the monitoring command. Another one is the top. Somebody likes the top command. So this command shows the similar, almost similar, but a little bit more information, like the when it's up and the how long this operating system is running. And load average is the average load. Last, I forgot there are three numbers. The first one is last minute, something like that, and the longer and longer. But you can check from the manual page the meaning of this one, and the task and one running and the other are sleeping. Is how many zombie? We talk about the zombie process. Okay, zombie usually is not a problem, and mostly the open the process to keep the resource. Then but zombie actually do not keep the resource, but it's on the process table. But you can check the zombie process and the CPU root time that has been here, the right hand side in the top VM state command and so on. So this is a memory space. This is a virtual memory space information. Then this one is the top. So ranked by the process that are using the resources. So you can see something. XORG is actually the X desktop. It's a graphical user the interface. So genome terminal is this one, and in it is the kernel process. You can see how many of them are using in memory space and so on. So very nice, but I like the VM state. In case you have the multiple processor, you can use the MP state, but I do not have the MP state command because this is a single CPU, the virtual machine. In case if you have the multiple processor, multiple CPU, or not multi-core, but multiple CPU processor, so you can use the MP state for the same as the VM state. So you can see the number of CPU at the same time. These two commands is the two best the monitoring command used in the real the work. Okay, then also such a demand and paging. So based on such a virtual memory and pages, so we can speed up to create the process. When we create the process, there are two systems, like two steps. One is a fork, another one is exec. For your reminder, fork means copy, and the exec assign the specific code of the child process. Then, as we have seen before, like the performance table between fork and thread, creating process and creating thread. Actually, creating process is really overhead. Why? Because allocate the memory, find the free space, and copy the data page by page to the physical memory. It requires I/O, so it takes the time. So when we process using the virtual memory, so we can get something benefit of that. That is called the copy on write. Copy on write means So if you go back to the shared, okay? Shared means what? We have only one page but can be shared by the multiple process. Right? So for example, the standard I/O is here. It can be shared by the multiple processes by updating only the memory, the MMU, the table, mapping table. Similarly, think about the fork. Fork actually copy it's a clone of the parent process, which means we don't have to create the new process, allocate the new one. Instead, just share. That makes sense because it's the same code, it's exactly the same thing. Instead of creating the allocate the new pages, we can just point to the parent pages. Then when really we write, copy on write, in case something changes, okay? In case something update or the new one like the EXIS or you can still keep the copy of your parents without the EXIS, but it may be changed in the middle of the process. Okay? Then we copy, which means copy means allocate the new pages. It's called the copy on write. So we can use the page on demand page to save the time. That's called the COW. Okay? Have you ever seen I think many of them use the free fork in your first project, right? What does that mean, the free? In the free fork, it's a virtual memory fork, copy on write. So if you are using the fork command, actually it copied, okay, except the data part, but it copied. But if you are using the free fork, it has during the fork, it's just update the page table only. That's the difference. That's called the free fork. Okay. However, if you are doing the EXIS, it's writing. Anyway, you need to write the program code for the child. So you need to need the new pages. This is called the copy and write, and you can actually get the better performance of to create the process. Any questions? Okay. So this slide shows how it works, the copy and write. So you can just share the first time that this is the child process, this is the parent process, but it's not actually use the new pages. Instead of just the point. Page A, B, C. However, if it's red, the vice versa. This is a parent, this is a child. If you write something, then you can update. At this time, even if you change only this part, this page, you can just write the new one. Okay, it's a page by page copy and write. So we actually implement based on this one. Then I didn't explain how to select the victim page. Victim page means in case it's a fault, there's the page fault, the track, or the invalid case. Then we need to exchange between the page frame and the virtual memory space. So page in and out. So which one will be out, which one will be in. So at the time, so to determine the victim page, there are different approaches. So page replacement is we need to page out the current one, then bring in. So this slide shows the concept of the high-level concept of the page replacement that I explained already. Okay. Then problem is how to select the victim page, victim from the physical memory. We have 15 more minutes. Okay. I little bit speed up to cover all the topic before semester end. Okay. So page replacement is in case it's invalid, we need to bring this page to the physical memory. However, in case we do not have enough space, how do you find whether you have the free page or not.
Index, invalid, and valid.
So we talk about free page frame management. We can have the list of the bit, okay? Then we can find the 0 or 1 to find the victim page. Please get the phone call outside. Okay? You can check the internet, but the calling is not accepted in the classroom. So, for the page replacement algorithm, it's so simple. We can decide one of the page frame as a victim page. Problem is how to decide. So to simulate this problem, we are going to use the reference string. Reference string means when you see this kind of number 1, 2, 3, 4, 5, 6. So let's say that we have the 5 pages. So 0, 1, 2, 3, 4. So actually each page has the information, number of the instructions, but we represent each page as the one number. So 1 means later you can think about the page number 1. Okay? Even though it has a huge, let's think about this 1 byte page size. Okay? You can consider 1 byte page size, and this is number 2, page number 3, page, and so on. So this is called the reference string, which means from the CPU needs the first page number 1, and next need the page number 2, page number 3, page number 4, page 1, again 2, and so on. So this is another example. It needs the 7. So we are going to two set of the reference string to demonstrate, to simulate such a page replacement algorithm. Before we start, our expectation is this graph shows what? The X means, which means bigger size of the memory, RAM. That means better performance. Better performance means less page fault. That's our expectation. Right? The bigger size of memory you have, the better performance we will get. The less page fault we will get. So that is our expectation, but not always true. Sometimes even though you have the bigger size of the memory, your performance will be down, which means the number of page fault sometimes increase. So which is called the Biliadis anomaly. So we will see such an example later. Okay. As I briefly introduced, always the first algorithm is based on what? First in, first out. Which means when you determine the victim pages, which one will be victim? Oldest one. Oldest one will be the victim. So this slide is a little bit confused sometimes. So let's check. We have the 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. This is a reference string, which means the CPU would like to read the page number 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5 in this order. Then, we have the, for example, this is the physical memory, page frame. How many pages we have? 3 pages. Okay, very small. Very small, the physical memory. Then, our program is maximum 5, so which means our logical memory probably like this order. Okay, so we'd like to read the CPU would like to read the data. So first, 1. What happened when CPU would like to read the data 1? Is there any page that include 1? No. Which means page fault. So you have the page fault first time. Then load, because it's on demand pages. So we need to bring the, actually this is not in virtual memory directly. You don't have to copy it to the virtual memory space. First time, you can just wait until it is needed. So one will be loaded into the memory, page by. But it's a very simplified, the example. Okay, then next, 2. Is there any 2? So we need to page fault. This is another page fault. I'm going to circle the page fault because this is to show the all the cases at the same time. This is actually time, but some of the students confused. So see this one. Actually, we have the only 3 page frame, not like the 2-dimensional array. So 2 is here. So this is up to the here. How many page fault so far? 2. And next 3, is there any? No. So 3 is here. So this is a page fault. A lot, not a lot. Some of the students forgot to count this one as a page fault. Really. So always several students. Please count this one also page fault. Then 4. Is there any? No. This is called page fault again. So we need to decide the victim, one of them, to make the free page frame. So our algorithm is first in, first out. Which one is the first in? 1. So 1 will be, what happened this time? Actually, this is a virtual memory space, swap space. 1 will be here. Okay, then the 4 will be loaded like this one. This is also page 4. Then, what about next one is 1? Page out and in. But this time to determine the victim page, oldest one, first in, first out. Which one is the oldest one? 2. So 2 will be here and 1 will be loaded into the memory. Okay. What about 2?
Not there.
It's not there. So page 4. So 2. This one is the oldest one, and 3 will be here. Okay? And what about the 5? 5 is not there, page 4 again. And which one is the oldest one? 4 and 5. What about 1? Yes, there is a pages, so you don't have to page in and out. No page 4. Just read it. Then next 2. Also, no page 4. 3. There is no 3. You need to decide the victim page. Which one will be? Oldest one. 5, 1, 2. So 5 is the oldest one. So 3 will be loaded, and this is a page 4.
1.
And 4, 1.
Yeah.
And 5, this one. So total how many page 4? You can just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So why 10?
So,
You missed one.
so
You missed writing.
like 5,
4 at the
1,
3.
2. When we were at 5, 1, 2.
So here, the last one is a 3, 4.
So when we were at 5, 1, 2.
I think let's see the 5, 3, 2.
Yeah, you missed
5,
there.
1, 2.
This one is 5.
Yeah.
5, yeah, 5,
I see. 5.
1, 2.
Here, the last one 3, 4. So last one is